The principle of equivalence is the idea that an observer in free fall so that would be an unaccelerated observer, an observer who's traveling along a time-like geodesic. For an observer in free fall, the observer can't tell by any local measurements or observations whether or not they're near a massive body. So let me draw a picture. In one case we have an observer, and let's put our observer in a rocket ship. So here's a rocket ship. Here's our observer. And in this case, the rocket ship is in deep space, far from any massive bodies, so it's just drifting in outer space, following a time-like geodesic. Notice the rocket engines are not firing. And in the other case, we have our observer near the surface of the Earth. So again, here's the rocket ship, our observer. In this case, again, the rockets are not firing, so the rocket ship and the observer are unaccelerated. They're traveling along time-like geodesics, and that geodesic might have the rocket falling directly towards the surface of the Earth, or maybe it's following an arc like this. But in either case, observer and rocket are following time-like geodesic. They're in free fall. The principle of equivalence says that this observer can't tell by making any local measurements or observations the difference between these two situations. In fact, not only can the observer not tell the difference, but there is no difference. So these two situations are equivalent. Now you might have noticed that I said the observer can't tell the difference between these two situations by making any local observations or local measurements. So this is true for local measurements. And that's why I put the observer in a little rocket ship. So the observer is confined to doing experiments and making observations within the rocket ship. Obviously, the observer here could just look out the window and see that they're near the surface of the Earth, but confining the experiments and observations to within the interior of the rocket ship, the observer can't tell the difference between this case, near the surface of the Earth, and this case, drifting in outer space. But this is still an important observation because our fundamental laws of physics are all local laws. And consider this observer drifting in outer space far from any massive bodies. This observer is following a world line in flat space-time. And we know how to do physics in flat space-time. That's just the physics of special relativity. We can even set up Minkowski coordinates and make our lives especially simple. So this observer can do experiments and make predictions using the physics of special relativity. And the principle of equivalence says this observer can do the same thing. So at least locally, this observer can set up a coordinate system that looks just like Minkowski coordinates. The space-time for this observer is flat, and all the results of any experiments and measurements this observer makes are identical to the results in this case. Let me give you an example of how the principle of equivalence can be used. Let's look at Maxwell's equations. All right, Maxwell's equations are the divergence of the electric field is equal to charge density, curl of the magnetic field minus time derivative of electric field is the current, J. The curl of E plus time derivative of B is 0, and finally the divergence of B is equal to 0. So these equations, of course, were formulated long before general relativity came along, but we know that they're compatible with special relativity. In fact, we can write this in the notation of flat space-time with Minkowski coordinates in the following way. Let's introduce the field strength tensor F mu nu, and F mu nu is defined in Minkowski coordinates as, well, the 0, 1 component is just the x component of the electric field, 0, 2 is the y component, and so forth, etc. The 1, 2 component is the z component of the magnetic field, the 2, 3 component would be the x component of the magnetic field, and so forth. All right, in terms of the field strength tensor, these two equations can be written as partial mu F mu nu equals mu naught J nu, where I've grouped together the charge density and the current into this J. All right, so this, again, this is in Minkowski coordinates for flat space-time, Minkowski coordinates. All right, and these two equations can be grouped together in the following way: partial alpha F beta gamma plus partial gamma F alpha beta plus partial beta F gamma alpha. And by the way, the indices here on F, the lower indices, the indices have been lowered from F with the upper indices by using the Minkowski metric, the flat space-time metric in Minkowski coordinates. So these are the equations that our observer, who's drifting in outer space, moving along a world line in flat space-time and using Minkowski coordinates, those are the equations this observer would use to describe any electric and magnetic phenomena. Right? But the principle of equivalence tells us that this observer can do the same thing. Even if this observer is near the surface of Jupiter or near the surface of a black hole. All right? And to use Newtonian language, this observer could be in a very strong gravitational field. But the principle of equivalence says this observer can also use these equations to describe electric and magnetic phenomena. These are local equations. They're a local set of differential equations describing how the electric and magnetic fields behave with various currents. Now, of course, in order to use these equations, our observer needs to set up Minkowski coordinates. Either one of these observers needs to do that. Of course, we don't always want to use Minkowski coordinates, but we know how to write down equations in a way that is independent of the coordinate system we use. So let's just rewrite these equations. First, for this equation, we can write as covariant derivative of F mu nu equals mu naught J nu. And likewise here, we'll just replace these partial derivatives with covariant derivatives. Del alpha F beta gamma plus del gamma F alpha beta plus del beta F gamma alpha equals 0. So now these equations reduce to these equations if we're using Minkowski coordinates, because in that case these covariant derivatives just reduce to ordinary partial derivatives. But written in this way, these equations are independent of what coordinates we use. So these are in fact the correct equations to describe electromagnetic phenomena in curved space-time. So these are the equations for electricity and magnetism in curved space-time. So notice we didn't have to invent new physics to describe electric and magnetic phenomena in strong gravitational fields. We just lifted what we know to be correct from flat space-time to curved space-time using the principle of equivalence. Let me give you another example that will help clarify what is meant by local observations or local measurements. So here's our observer in the rocket ship. The observer and the rocket ship are in free fall, so the engines are not firing. And the observer does the following experiment. Take two tennis balls, stretched out at arm's length apart, and then let them go, and watch what happens. Well, if the observer is out in empty space, far away from any massive bodies, what will happen is these two tennis balls will just drift along right beside the observer. And in particular, the two tennis balls will maintain the same distance apart from one another. On the other hand, if the observer does this experiment near the surface of the Earth, then what will happen is the observer will see the two tennis balls begin to drift towards one another. And the reason is because as the rocket ship, observer, and tennis balls are in free fall towards the center of the Earth, the balls want to fall towards the center of the Earth. If this is the center of the Earth, then they want to fall in a radial direction. So as the observer and tennis balls fall towards the center of the Earth, the two balls move towards one another, and the observer can see that happening. So of course there is a difference between drifting in outer space far from any massive bodies and free falling near the surface of the Earth. But in order for the observer to see that difference, the observer has to do a non-local experiment, have the balls separated by some distance, and wait for some period of time to see the two balls start to drift together, in the case near the Earth. Right? So the point is, no matter how sensitive the observer measuring devices might be, or how observant the observer might be, there's always a limit. If the balls are too close together and the observer only watches them for a short period of time, then the observer can't tell the difference between being near the surface of the Earth and being in far outer space. So that's what's meant by local, is there's always a sufficiently small region of space and a sufficiently small duration of time in which the observer can't tell the difference between being near a massive body and drifting in outer space far away from any massive bodies. From a space-time point of view, the principle of equivalence says the following. We have an observer who's traveling along a time-like geodesic. So the observer is in free fall, unaccelerated. And for this observer making local measurements, they can't tell the difference between being near a massive body, or to say it in Newtonian language, to be in the presence of a gravitational field, and drifting out in outer space where there are no gravitational fields. So to this observer, all the physics looks like the physics of special relativity, of flat space-time, and the observer can even set up a Minkowski coordinate system. Maybe I can draw a little coordinate grid here to represent the Minkowski coordinate system. So these are locally Minkowski coordinates. And in these coordinates, the metric in this region will look just like the metric for flat space-time in Minkowski coordinates. So that's -1, 1, 1, 1 along the diagonals. And by the way, we often denote this metric as eta mu nu, Greek letter eta. Said a little bit more precisely, it's always possible to find a set of coordinates in a small region around a time-like geodesic in which the metric on that geodesic has the form of the flat space Minkowski metric, the eta mu nu. But then away from the geodesic, there can be modifications of this. So we have the actual form of the metric in this region near the geodesic is eta mu nu plus small terms or small corrections. And how small these are? Well, they depend on how big your region is. And whether or not they're important depends on how fine your measurements are. But it's always possible to find a sufficiently small region in which these small terms can be ignored, and the metric looks just like the metric for flat space-time. And by the way, another name for these locally Minkowski coordinates is Fermi normal coordinates. What I'm going to do next is show you explicitly how the observer constructs these Fermi normal coordinates. Now, the derivation isn't easy, but I think it's worthwhile because there are a lot of interesting lessons that you can learn by going through the analysis. So we begin with the time-like geodesic. So it's parameterized by proper time tau. And just to emphasize that this is a time-like geodesic, I'm going to put a little subscript TL here for time-like. So the subscript TL means this is a time-like geodesic. And remember, for a time-like geodesic or any time-like world line, we can define the forward velocity as the derivative operator d by d tau, and the components of the forward velocity then are just the derivatives of these functions x mu sub TL with respect to proper time tau. And the forward velocity is, since this is a geodesic, the acceleration is 0. The acceleration is defined by u alpha del alpha u mu. And this equation just tells us that the forward velocity vector is parallel propagated along this world line. All right, so here's the forward velocity at each point along the world line, and its covariant derivative is 0, which means when we parallel transport this vector back to here, that the transported vector coincides with the vector that's already there. Now, the first thing that the observer needs to do is set up an orthonormal basis at each point along the world line. Now, an orthonormal basis is a set of vectors, of 4 different vectors at each point that span the 4-dimensional spacetime. And the observer is going to use u as one of the legs of the basis, of the orthonormal basis. So that will be one of the 4 different vectors at each point. And to obtain the other vectors, the observer does the following. Let's say at this point right here, the observer picks out 3 space-like vectors. Let's call them E1. So the components of E1 will be E1 mu and E2 with components E2 mu. And of course, I can't really draw in 4 dimensions here, but I'll go ahead and draw another vector, E3. Right, so these 4 vectors are all orthogonal to each other, and they're all normalized. Okay, so that means normalized, of course, for u means the norm, the square of the norm is -1, as it always is. And for these vectors, let's collectively refer to these as E mu A, where the index A just labels which of these basis vectors I'm talking about, either the first, second, or third. All right, so these vectors are orthogonal to each other and normalized. So E mu A, G mu nu, E nu B is equal to 1 if A and B are the same, or 0 if A and B are different. So that's the Kronecker delta AB. And finally, we also insist that these vectors should be space-like. In other words, they should be orthogonal to the forward velocity u. So we have u mu, g mu nu, e nu a. So for each of these 3 vectors, it's orthogonal to u. So at this point, these 3 vectors, E1, E2, E3, and u, form an orthonormal basis. Now, what about these other events along the world line? What does the observer use as an orthonormal basis at these other points? Well, we already know that one leg of that orthonormal basis is u, but what about the other legs, the e's? Well, what the observer does is define the e's at each of the future points along this world line by parallel transporting these basis vectors e1, e2, and e3. So we define e1, e2, and e3 at future points along the world line, future events, by parallel transport. All right, so we have now a field of vectors E1 all along the world line, and that field of vectors is defined by parallel transport. So in particular, U alpha del alpha E1 is equal to 0, and of course the same is true for E2 and E3. So for each of these three vectors, this is just the statement that the covariant derivative along the world line vanishes, which is to say that the e's are parallel transported. So with the e's defined this way, what we need to show is that the basis formed from u and e is orthonormal all along the world line. And that's not hard to show. Let's start with this condition that u and e are orthogonal. We can compute the inner product of u and e, and we know by construction that this is equal to 0 at the initial event here where the e's were first constructed. In order to show that it remains 0, we just need to show that the tau derivative, the derivative of this along the world line, vanishes. Right? Now the derivative of a function along the world line is just u alpha covariant derivative alpha of the function. That's u mu g mu nu e nu a. And now we can use the product rule to write this as u alpha del alpha u mu times g mu nu e nu a plus u alpha del alpha g mu nu times u mu e nu a plus u alpha del alpha e nu a times u mu g mu nu. Right? Now you'll notice, of course, this is equal to 0 by construction of the way the e's were constructed all along the world line. This is equal to 0 because it's just the acceleration. And finally, this is equal to 0 because the covariant derivative of the metric is always 0. All right, so what we've shown is that this quantity, the inner product of u and e, it's 0 at one point, and its derivative along the world line is 0, so it must be 0 at every point along the world line. And by the same kind of calculation, you can show, of course, that the e's remain orthogonal to each other and normalized. Just take the covariant derivative or the derivative along the world line of this quantity and rewrite d by d tau as u alpha del alpha, where del is the covariant derivative. Then the covariant derivative acting on each of these three factors gives 0. All right, so with the basis constructed in this way, it's an orthonormal basis, and it's orthonormal all along the world line. So we can complete our diagram by adding little E1, E2, and E3 vectors all along here. E2, E3, E1, and so forth. So E1, E2, E3, along with the velocity vector u, form an orthonormal basis that the observers can use. And notice that because the e's are orthogonal to u, they're space-like. These e's are space-like, meaning they span events that are seen as simultaneous by the observers. They span simultaneous events. At each point along the world line, they span a set of events that are seen as simultaneous by the observers. And physically, the way the E's are realized is by a set of gyroscopes. So a gyroscope will maintain its orientation as long as there are no torques acting. So that condition is just mathematically the condition that the axis of the gyroscopes are parallel transported along the world line. So the way these observers set up these basis vectors is by taking a set of 3 gyroscopes that are initially orthogonal to each other, and then they parallel transport them into the future. In other words, they just carry them along without exerting any torques on them. And the axes of those gyroscopes will continue to define the direction of these basis vectors, the EAs. Let me summarize the results so far. We have an observer who travels along a time-like geodesic x sub TL, of course parameterized by proper time tau, and the observer sets up basis vectors. One of those basis vectors is just the velocity of the observer, and then the E's, the EAs. And all of these basis vectors are parallel propagated along the world line. So in other words, for U, we have U alpha del alpha U mu equals 0. This, of course, is just the condition that the acceleration is 0, which tells us that the world line is a geodesic. And we know from our past calculations that we can write this as x mu double dot, and I'll put the little TL subscript here, plus gamma mu alpha beta x dot alpha TL, x dot beta TL. And of course the Christoffel symbols here are also evaluated along the world line, so I'll put a little evaluation symbol here along the time-like world line. So this is one equation that we'll need later on. And we also know that the EAs are parallel propagated, so that's U alpha del alpha E mu A equals 0. And if we expand this, U alpha is of course partial x alpha sub TL with respect to proper time, and the covariant derivative then is partial alpha E mu A plus gamma alpha mu beta E beta A. Now this factor combined with the d by dx alpha using the chain rule just gives us the derivative with respect to proper time acting on E mu A. So that's E mu A dot. And for this second term we have Christoffel symbols. Of course those will be evaluated along the time-like world line, times this factor, which is x alpha dot along the world line, times E beta A. So this and all of this, of course, equals 0. So this is another equation that we'll need later on. Now the observer wants to use these basis vectors to assign coordinates to events near the world line. So here's how they do it. Here's the world line, x mu of tau, with a little subscript TL for time-like. Pick a point, and let's call this point O, that's a script O for observer. And from that point, send out a space-like geodesic. So this is a space-like geodesic. And we'll give it the coordinates x mu of s, so it's parameterized by proper distance s, and we'll put a little SL subscript for space-like to distinguish it from this time-like geodesic. All right, now the tangent to this geodesic, let's call it t. So t is just the derivative operator d by ds, and the components of t are just the derivatives of x mu sub SL with respect to proper distance s. Now, we don't want this curve to be just any space-like geodesic. We want it to be a set of events that the observer sees as simultaneous. So in other words, we want the tangent vector t to be orthogonal to the velocity of the observer. And that means this tangent vector lies in the subspace spanned by the basis vectors, the EAs. So we can expand this vector t in this basis, the EAs. So in other words, we can write t mu as a linear combination of E mu A, and the coefficients in that linear combination I'll just call TA. Now let's pick a point along this space-like geodesic. Let's call this point P, and this event will have coordinates x mu along the space-like geodesic for some particular value of s, for some particular value of proper distance s. All right, so we can write the coordinates of point P, that's just x mu sub SL of s for some particular value of s. And we can expand this in a Taylor series about s equals 0. So we'll write this as x mu SL of 0 plus x mu dot, where the dot denotes d by ds, evaluated at 0 times s plus 1/2 x mu double dot sub SL evaluated at 0 times s squared, and so forth. Now this first term is just the coordinates of the space-like geodesic at s equals 0, and I'll assume s equals 0 corresponds to the point O here. So this is s equals 0. So this is just coordinates of the point O. This is the tangent vector defined right here, the tangent vector at O. So that's t mu at the point O. And for this term, x double dot, remember the space-like geodesic satisfies the geodesic equation. So the geodesic equation says x double dot mu sub SL plus gamma mu alpha beta all along this space-like world line, space-like geodesic, times x dot sub SL alpha x dot sub SL beta. And we can now evaluate this equation at s equals 0. Okay, so at s equals 0, let's move this term to the other side. We have x mu double dot sub SL at 0 equals minus gamma mu alpha beta at that point s equals 0, which is the point O, times, now this is the tangent vector evaluated at point O. So everything is evaluated here at the point O. All right, so now if we put all these together, we have an expression for the coordinates of point P, which is x mu at point P is x mu at point O plus t mu times s, and that's about evaluated at point O, minus 1/2, now I'm writing this term right here, there's a 1/2 and an s squared, all times this. We have gamma mu alpha beta t alpha t beta all of that evaluated at point O times s squared. And of course, there are higher order terms as well. Now let's use the fact that these tangent vectors at point O can be expanded in a basis of the EAs. In fact, I should have emphasized when I wrote this down that this expansion only holds at point O. After all, the EAs are only defined along the world line. So this is just an expansion at point O for the tangent vector there. So writing T mu at point O as TA times E mu A, we have the coordinates at point P equals the coordinates at point O plus TA times S times E mu A minus 1/2 gamma mu alpha beta at point O times TA S TBS times E alpha A E beta B, and plus of course higher order terms. Now let me introduce a shorthand notation for this combination TA times S. Let me call that X bar A. Right, so the coordinates at point P are the coordinates at point O plus X bar A times E A mu minus 1/2 gamma mu alpha beta at point O times X bar A X bar B times E alpha A E beta B plus higher order terms. I derived this result by picking a particular point O along the time-like world line, and of course the coordinates of that point depend on the choice of O, and also notice that the basis vectors depend on which point I've chosen. So just to emphasize that, let me show that we're evaluating these basis vectors, the EAs, at point O. And of course the Christoffel symbols also depend on which point O that I've chosen. On the other hand, these XA bars don't depend on the choice of point O. Okay, they were chosen independently of that choice. So we can rewrite this equation in a way that emphasizes that it holds for any choice of the point O by writing this as the coordinates along the time-like world line of some point which we've given the parameter value tau. So that's just another notation for some particular point along the world line. Then, of course, EA mu also depends on which point along the world line we're talking about. The Christoffel symbols depend on which point along that time-like world line we're talking about. So we're evaluating those at XL, X sub TL of tau. We have the X bar A, X bar B, and E alpha A depends on tau, E beta B depends on tau. And then there are higher order terms. So written this way, we have the coordinates of some point P, and those coordinates depend on which point along the world line we're talking about, which is parameterized by tau. And the coordinates also depend on the choice of these XA bars. So we'll write this as X mu of tau, which depends on tau and the X bars. And these are the coordinates of point P. Now let's define a new set of coordinates for point P. So these are the Fermi normal coordinates. And they're just the tau and X bar A. Right, so this equation defines the coordinate transformation between the new coordinates tau and X bar A and the old coordinates X mu. So what the observer is doing is assigning new coordinates to the point P, So here's the observer's world line, and here's the point P. The observer assigns coordinates to this point by sending out a geodesic from the world line to point P. And this geodesic is purely space-like in the sense that the tangent to this geodesic is orthogonal to the velocity of the observer, or said another way, these events are viewed as simultaneous by this observer. So since these are simultaneous events, the observer assigns a time-like coordinate to this event, which is just the proper time that the observer observes on their own clock at this event. So the time-like coordinate is just tau, and for the space-like coordinates, the observer looks at this tangent vector and decomposes it in the EA basis. So here's the basis vectors E1, E2, E3. And then the components of this vector in this basis, the components are TA. And if this is the distance, the proper distance here is S, then the space-like coordinates are what I've called XA bar, which is just these components TA scaled by the proper distance S. So TA is just giving the direction to this point, and S is giving the distance. These are Fermi normal coordinates. And what we need to do now is to show that in these coordinates, the metric is just the metric of flat space-time and Minkowski coordinates. So we do that by looking at our coordinate transformation. So x mu is, these are the old coordinates of the point P as functions of the new coordinates, tau and x bar. This is the coordinates of some point along the world line, the time-like world line, plus x bar a EA mu, which depends on tau, minus 1/2 Christoffel symbols, gamma, mu, alpha, beta, which depends on which point we're at along the world line, times x bar a, x bar b, EA alpha of tau, EB beta of tau, and of course higher order terms. So let's collect together these new coordinates and call this x bar mu. The way we find out what the metric looks like in the new coordinates is we first expand the metric in the old coordinate basis, so that's g mu nu dx mu dx nu, and then we expand the metric in the new coordinate basis, so we'll call the new components of the metric g bar dx bar mu dx bar nu. All right, now using the chain rule here, we have g mu nu times partial x mu with respect to x bar, say alpha, times dx bar alpha, and dx nu can be written as partial x nu with respect to x bar, say beta, dx bar beta. All right, so that's equal to g bar dx bar dx bar. Let me write that as g bar alpha beta dx bar alpha dx bar beta. And now we see we have common factors of dx bar alpha dx bar beta. So in order for this equality to hold, we have g mu nu times partial x mu with respect to x bar alpha, partial x nu with respect to x bar beta is equal to g bar alpha beta. So this tells us what the new components are, the components in the new coordinate system, in terms of the components in the old coordinate system. And these derivatives we can just compute from our coordinate transformation rule here. Let's go ahead and do that. Let's start with the derivative of x with respect to tau. So let me repeat the definition here of our coordinate transformation. And Before I start computing, let me point out that this expansion is an expansion essentially in x bar a. So the Fermi normal coordinates only cover a small region near the world line, only a local region near the world line of the observer. So the proper distance to that point P is always small, and these x bar a's are always scaled by the proper distance. So these are the small quantities. So this term is of order 1 in x bar a's, this term is of order 2, and these terms are of order 3 and higher. So now let's compute partial x mu with respect to tau. So here we have the partial of x along the time-like world line with respect to tau, but that's just the components of the 4 velocity of the world line. The next term is x bar a times the tau derivative of Ea mu. And then here we have terms where we compute the derivative with respect to tau of the Christoffel symbols and these basis vectors, but these terms are of quadratic order in the x bars, so I'm going to ignore those. ... These are terms of order x bar a squared and higher. So now remember that these basis vectors are parallel transported along the world line, and that told us that Ea mu dot plus gamma mu alpha beta u alpha E beta vanishes. So we can write partial x mu with respect to tau as u mu minus gamma mu alpha beta u alpha x bar a E beta a plus higher order terms. Now let's compute the derivative of x with respect to x bar a. So let me repeat once again the definition of the coordinate transformation. And what we want to compute is partial x mu with respect to x bar a. But notice I have some repeated indices a here as well as here, so I don't want to confuse this a with those a's, so why don't I change this to the letter C. And now for the first term, this is independent of x bar, so that just gives 0. For this next term, we have the derivative of x bar a with respect to x bar c is Kronecker delta ac. So it's just 1 if a is equal to c, it's 0 otherwise, times E mu a. And for this next term, we have Christoffel symbols times derivative of x bar a with respect to x bar c, that's Kronecker delta ac, x bar b, E alpha a, E beta b, and minus 1/2 gamma mu alpha beta x bar a delta b c. So that's differentiating x bar b with respect to x bar c, E alpha a, E beta b, plus higher order terms. All right, there's a sum over a, so this is 0 unless a is equal to c. So we have E mu c minus, now this term, we have a sum over a, so that converts this index to a c. So why don't I just do that here? We'll cross out this Kronecker delta and make that a c. And likewise in this term, we can cross this out and make that a c. Now, it should be pretty clear at this point that these two terms are actually the same. They're equal to one another. Remember, the Christoffel symbols are symmetric in their lower indices, so it doesn't matter when you wire something with a lower index, it doesn't matter which one of the indices it's wired to. So in this first term, we have a free index C, and it appears on an E, which is then wired with the Christoffel symbols, and the other index on the Christoffel symbol is wired to this other factor of E, which in turn is wired through this index B to x bar. Right? So we have the same pattern here, starting with the free index C. It's wired through E to the lower index on the Christoffel symbols. The other index on the Christoffel symbol is wired to another E, which in turn is wired to X bar. So apart from some renaming of the indices, these two terms are equal. So let's just write this as a single term, gamma mu alpha beta X bar B E beta B and E alpha C. And then there are higher order terms that are quadratic in the spatial coordinates, the X bars. And just to be clear, let's remember that these Christoffel symbols are evaluated along the world line, so they just depend on tau. So now let's put this together with our previous result. And again, here I should emphasize that this is evaluated along the world line, so it just depends on tau. Let's put these together to compute the components of the metric and the Fermi normal coordinates. So we can compute g bar tau tau. That would be g mu nu partial x mu with respect to tau, partial x nu with respect to tau. We can compute g bar tau a. That would be g mu nu partial x mu with respect to tau, partial x nu with respect to x bar a. And we can also compute g bar ab. That would be g mu nu partial x mu with respect to x bar a, partial x nu with respect to x bar b. So let's just pick one of these as an example. Let's compute this one, g bar sub tau a. So g bar tau a is g mu nu partial x mu with respect to tau, partial x nu with respect to x bar a. So that's g mu nu, this first factor, partial x mu with respect to tau. We can remind ourselves of what that looked like. It's this expression. So that's u mu minus gamma mu alpha beta u alpha x bar. And let's see, I don't want to use the letter A because I have A as a free index here, so let's use the letter B. That's wired together with E beta B. Okay? And then this term, and of course there are higher order terms that I'm going to drop. And then this term is from right above, we need to change the mu index to a nu, and we need to change the C index to an A. So this is E nu A minus gamma nu. And now these repeated indices alpha and beta, maybe I should use different letters here so I don't confuse them with these alphas and betas. It's called as sigma and rho. Then we have X bar B. Well, I've already used B here. Why don't I use C here, EC, and then we need to wire this with one of the indices on the Christoffel symbols. And then we have the other index on the Christoffel symbol. That would be E is sigma. That's E sigma. And this index is the free index, so that's the one I'm calling A here. And then there are higher order terms. All right, so here's the expression for G bar, the tau A component of G bar. And before we go on, let's be careful here. This G mu nu is G mu nu at the point P, so it's the components of the metric in the original coordinates, the big X's, and those in turn are functions of our new coordinates tau and x bar. So let's remind ourselves of what this looks like just from right here. It's the coordinates of the point along the world line, x, TL. Let me go ahead and put an index there, not to be confused with the index here. It's just, this is in the argument of the functions, plus x bar, let me just use a different index here, d, ed mu, and then higher order terms. So we can now expand this in a Taylor series. This is just x mu evaluated along the world line, plus the derivative of g with respect to x times the small perturbation here. So we can write that as partial, let's say alpha g mu nu evaluated along the world line times the small quantity x bar d e d alpha. And then there are higher order terms in the expansion. Right, so if we put that together here, we have g bar tau a is equal to g mu nu, and now I think I'll stop writing the evaluation along the world line symbol, plus partial alpha g mu nu x bar d e alpha d, plus higher order terms that I won't write. We have u mu minus gamma mu alpha beta u alpha x bar b e beta b, plus higher order terms. Then e nu a minus gamma nu sigma rho x bar c e rho c e sigma a, plus higher order terms. So this looks like a bit of a mess, but remember, we're only writing everything to first order in small quantities, to first order in these spatial coordinates. We're dropping anything that's quadratic or higher in the spatial coordinates. So we don't have too many terms here. The terms that are independent of the spatial coordinates are g mu nu times u times e, u mu times e nu a, and then we have terms that are linear in the spatial coordinates. Let's start with g mu nu times u times this linear term. So that would be minus, let me put the minus sign there, gamma nu sigma rho x bar c e rho c e sigma a. We have a term linear coming from g mu nu times this linear term. So again, there's a minus sign, gamma mu alpha beta u alpha x bar b e beta b, then times the constant term here, constant in the spatial coordinates, e nu a. And finally, we have this term, partial alpha g mu nu x bar d e alpha d times u mu times e nu a. And then there are higher order terms. All right, so first of all, this is just the inner product of u and e, but by construction, the basis vectors are orthonormal, so this is 0. So now let's take the remaining terms and let's write the Christoffel symbols in terms of derivatives of the metric. So we have for this first term, and we have a minus 1/2 coming from the definition of the Christoffel symbols. So I'll write that 1/2 out first. So we have g mu nu, u mu, then here we have 1/2, I've already written, g nu, and let's come up with another Greek letter, say gamma, times partial sigma g rho gamma plus partial rho g sigma gamma minus partial gamma g sigma rho. Then we have x bar c ec rho e sigma a. So that's the first term. The second term is similar. We have a 1/2 coming from the definition of Christoffel symbols. We have g mu nu here. We have g mu, say gamma, times partial alpha g beta gamma plus partial beta G alpha gamma minus partial gamma G alpha beta. We have a U alpha X bar B E beta B E nu A. And then the final term we'll just write as is. That's partial alpha G mu nu times X bar D E alpha D U mu E nu A. And then higher order terms. All right, now this really is a mess. But if we examine these closely, we'll see that it's not really so bad. First of all, the G mu nu here and the G nu gamma here gives us a Kronecker delta mu gamma. And then contracting with the gammas in here, we'll just convert those gammas into mu's. So let me cross these factors out and replace the gamma here with mu. Gamma is replaced with mu. And likewise, here we have a Kronecker delta nu gamma, and then summing over gamma converts these gammas into nu's. And now I think that we can see that a lot of these terms cancel. In fact, they all cancel. So let's start with, for example, this term. This term has a partial derivative with an index mu, and it's wired with a velocity u here. And we also have a similar term here where the partial derivative is wired, has an index alpha wired with this u. Now the other two indices here, one of them is wired with an e that has the free index a. The other index is wired with an e that is in turn wired with a spatial coordinate x bar. And we have the same pattern here. We have the indices beta and nu, and one of these is wired with an e with a free index a. Doesn't matter which one because remember G is symmetric. The other index is wired with an e that is in turn wired with a x bar. And we have a minus sign here and a plus sign here. So you can see that these two terms cancel. So similarly, if we take a close look at, say, this term, which one do I want to do next? Well, let's go ahead and look at this term. This term, and I need to, of course, cross these out because I use those to replace gamma with nu here. So now look at this term. This term has one of the indices on, well, the partial derivative has an index that's wired with an e that is in turn has the free index a on it. Okay, and of these other two indices on G, one of them is wired with a velocity u, and the other is wired with an e that is itself wired with a spatial coordinate. So we should see the same pattern in one of these terms up here. All right, this term, you see the index on the partial derivative is wired with an e with the free index a, and these other two indices, rho and mu, one of them is wired with a velocity, and the other is wired with this combination, e, that is in turn wired with the spatial coordinates. So you can see that this term and this term cancel. And now the remaining terms here, they're actually equal to one another. So we have one of the indices on the metric here is wired with the velocity. The derivative is wired with the e that is in turn wired with the spatial coordinate, and the other index on G is wired with the e with the free index. So similarly here we have one of the indices on G is wired with e with a free index. The other index on G is wired with the velocity, and the index on the partial derivative is wired with the e that is in turn wired with the spatial coordinate. So these two terms are the same, and they're in fact the same as this term. Okay, so again, one of these indices on G wired with u, the other index wired with the e with the free index a, and the alpha coming from the partial is wired to this combination. So in this way we can see because there's minus a half and a minus a half, that these two terms together cancel this term. So what we've shown is that the tau A components of the metric in the Fermi normal coordinates are equal to 0 plus higher order terms. And all of these terms are at least quadratic in the spatial coordinates. So these are all quadratic and higher in the spatial coordinates, the XA bars. So I think I'll leave it up to you to verify that the tau-tau component of the metric is just minus 1 plus higher order terms, quadratic and higher, and the AB component, these components are just 1 if A equals B, 0 otherwise, plus higher order corrections. So what this shows is that in Fermi normal coordinates, the metric has the form of the flat metric in Minkowski coordinates plus higher order terms, quadratic and higher, in the spatial coordinates. Now, one immediate consequence of this result is that the Christoffel symbols in Fermi normal coordinates vanish along the world line. So let's write the Christoffel symbols in Fermi normal coordinates as gamma bar alpha beta mu. So this is 1/2 the inverse metric in Fermi normal coordinates times partial alpha g bar beta nu. And now let me use the symbol partial bar to denote derivative with respect to the Fermi normal coordinates, plus partial bar beta g alpha nu minus partial bar nu g alpha beta bar. All right, if we evaluate this along the world line, the time-like geodesic, then these are all derivatives with respect to the x bars, but because, and of course this term gives 0, but these terms are all quadratic. So when we differentiate, all of these terms are linear in x bar A. And when we evaluate on the world line, where the spatial coordinates are 0, we find all these linear terms go away. So gamma mu alpha beta bar evaluated on the world line is equal to 0. In turn, the vanishing of the Christoffel symbols tells us that covariant derivatives in Fermi normal coordinates are just ordinary derivatives. So if we have a covariant derivative acting on a tensor, so t bar are the components of the tensor in Fermi normal coordinates, and there's a bunch of indices here, this is just equal to the ordinary derivative of the tensor components, ordinary derivatives using Fermi normal coordinates. So an observer traveling along a time-like geodesic, that's an observer in free fall, can always use Fermi normal coordinates, and in those coordinates the metric will look just like the flat metric in Minkowski coordinates, and covariant derivatives are ordinary derivatives. So an observer can use all of the machinery of special relativity, all of the formulas and relationships from special relativity, to describe the physics locally along the world line.